Let's talk about comparator circuits. Sometimes it's handy to have an analog, electronic, if statement. The way that would work is it would compare two voltages. If V plus was greater than V minus, the output would be a logical high. If V minus was greater than V plus, the output would be a logical low. Here we have an op-amp circuit that does that for us. It's powered by a high voltage VCC and a low voltage VEE. When VI is positive, the output's VCC, and when it's negative, it's VEE. Sometimes it's handy to have a comparator that has hysteresis. Hysteresis is something you're familiar with if you understand how a thermostat works. A thermostat is the thing that turns on and off the heater in the house. If you have your thermostat set at 68 degrees, the heater won't actually turn on until the temperature gets to something like 66 degrees. When the temperature increases because the heater's been turned on at 66 degrees, it'll get up to 68 degrees, but the thermostat does not turn off the heater yet. It just waits until it gets up to 70 degrees. And when it finally gets to 70 degrees, it does turn off the heater. Then the room cools down, and when it gets back down to 66 degrees, the heater will get turned on again. Without hysteresis, if you just used a simple comparator to turn on and off your furnace, it would go on, off, on, off, on, off, on, off, and it would be very annoying, and it would also wear out the circuitry that was turning on and off the furnace and probably not be good for the furnace. Let's look at how we could make hysteresis in an op-amp circuit like this one. So here we have the same comparator that we had above, and we've added two components. R2 provides positive feedback between the output and the input terminal, right here at this positive terminal, and the input is now moved over here on the other side of R1. So essentially now the output has some effect on when this thing will turn off and on. The Vs here is effectively fighting with V out about what the voltage at the positive terminal of the op-amp is. V out will either be VCC or VEE. So there are a couple of voltages that will cause this thing to switch. One of them when V out is VCC and one of them when V out is VEE. And the switching occurs when this node right here at the positive terminal of the op-amp is 0. There's a little question down here. It asks, what does the input-output characteristic look like for the comparator with hysteresis? Let's try and answer that. Well, the important thing to note is what Vs is going to cause the thing to switch from one side to the other. Well, that happens when Vi equals 0. So what I'm going to do is I'm going to assume Vi is 0, and I'm going to write a node equation right here at the non-inverting input of the op-amp. So if you look at this first term in the equation, it's just the current coming in from the Vs source on the left, Vs minus Vi over R1. The next term right here is the current coming in from the output side, V out minus Vi over R2. You can see that right here. If we set those two equal to 0 and solve, we'll get for an answer for the voltage Vs that causes a change to happen. And in general, it's minus V out R1 over R2. Recalling that V out has two values, either VCC or VEE, we actually get this final equation for the switching voltage at which switching occurs. So let's look and see what that curve might look like. Here we have Vs on the x-axis and V out on the y-axis. Let's assume we start out with the output at VEE because the input was very negative over here. So as we now increase Vs, we move along this line right here. At this point right here, both Vs and the output are both negative, so they both agree about what Vin should be. It should be negative, and means it's not going to switch yet. Now when we get over here, Vs is now trying to change the input to a positive voltage, but at this point, the output is still too strong for Vs to do it. However, right here at this Vs value right here, what happens is the input voltage is 0, and any Vs greater than that will switch it over to the positive output voltage, VCC. Now if we were to take this Vs and now start decreasing it back this way, we'd get back here, we'd get to the point where it switched before, but it won't switch there, it just keeps going. And won't switch where Vs is 0 or Vs is slightly negative. You have to wait all the way over here where Vs is minus VCC times R1 over R2, and then it switches down and goes here. Notice the direction of the arrows. This arrow right here is pointing to the right, this arrow points up, this arrow points left, and this arrow points down. That is the direction that the travel occurs as you increase or decrease Vs.